Yeah, so the title of this session is the quantum and the gravity. So I suppose there is nothing else beyond that that we can discuss here. And from foundations to experiments, so again, like, encompassing everything basically. Yeah, so in particular, I think these topics encompass not only the talks of today, but also the talks of yesterday and the day before. And in fact, it was mentioned yesterday that some of the discussions can be postponed to today. So maybe the questions and all that can be directed to the speakers here, as well as to the speakers of the previous days, basically. Okay. So first, maybe the speakers on the podium, they can you can maybe give a short 2-minute, 3-minute, 5-minute summary of your presentation, or in fact just to set up the stage, what you think is important, like what message you want to kind of deliver, and what is the thing that you would like to discuss, basically, just to set up the stage for the discussion. So maybe from
I'll probably take less than 5 minutes. I have a nice way to summarize what I found, which I use the interpretation of these are the space-time coordinates. I suppressed the angle, so now it fits on a piece of paper. But the nice thing I can do here is to show what I've actually done, which is that these regions 1 and region 2 have to be identified. So what you get is this. In this picture, when you fold it together properly, you find that every point of the radial diagram is now represented twice here in one sheet and in the other sheet, but they are identified. So in this picture, they are identified at the cost of having a conical similarity here. And actually, conical similarity is physically speaking not so terrible. The conical similarity is physically speaking not so terrible because it's aromatic. You can smoothen it, and then it represents, I think it represents all matter that ever went through the black hole or ever will come out, and which generates strong curvature. That's a strong curvature of this thing. But more importantly, if you now add the angles theta and phi, you get a two-dimensional sheet of these points. And that sheet in many respects looks like a string theory. So it looks like a string, but a string with a very strong string constant, so big that it's the curvature it generates gives you an angle of 180 degrees, which makes it every point here is twice in the original flat. So that is sort of the remarkable thing, and then you can. When you do this, you find that the blue line occurs twice and the green line occurs twice in this picture. So they should be folded together, as I tried to do, but here it's not so easy to do. But the realization of that is that now you have only one region of everything going in and one region of everything going out. We have region 1 that you see here is completely representing the entire region outside the black hole. Region 2 is just a mirrored image. Together they form a perfect combination of a black cat, which you encounter when you write out a density matrix instead of a matrix. So it looks as if the black hole, if you treat it this way, generates the full density matrix of the state around the quantum states. The density matrix contains the quantum states already squared, so you don't have to square it again in order to get the probability of something, but it is the output of the density matrix itself. And this means that the inverse temperature that one beta and produce defines 1/8 pi times the mass of the motion. But here you get only half of that, because I don't have to square density matrix to get the probabilities. And that gives you that now my problem is either square root or Hawkins. That means that the temperature is now getting affected too. So I disagree with Hawking about the temperature by factor 2. I think that's an important thing because factor 2 in temperature makes enormous amount of difference, as you know. And it's like room temperature and burning your hands if you try to touch something. So it's a big effect. And it's important to get all the deep mathematical details right. In particular, the fact that information always returns. Information that's fallen into a black hole has no other place to go than out from the other side, but out into the same real world as it went in. So it's not like what Hawking thought, that ingoing radiation will emerge somewhere else in the universe. It will emerge backwards in time. We forgot to mention that, but that's also happening. So it's a rather extreme situation, but I think the mathematics comes out beautifully. And I was surprised how precisely and effortless the unitarity seemed to come out. Except for one thing, and there's a very important negative note that I have to mention, is that gravity is totally colorblind. So the gravitational force only feels mass and energy or energy momentum, but it doesn't feel color. So if you want to have the entire standard model there, it has all colors, well, the three colors for SU3, it has the weak colors for SU2 and so on. All these are colors not seen by a gravitational field. So we have to be very careful in doing this part of the calculation right. I haven't finished that yet. I'm still wondering whether demanding just unitarity of the exchange matrix, whether that will do the job entirely, or do we have to be more careful and make modifications in the standard model so that it fits. What I hope is that something like that will happen, that the standard model might have to be modified in order to get things exactly right. And if that modification just means a slight change in coupling constants or masses and so on, then that will be a new prediction for the standard model, that the actual values are so and so as follows from comparing standard gravity with black hole gravity. So I think there's lots of stuff to be done in the future. But I think the picture I've generated now looks quite nice to my taste.
I think I totally agree with Professor Hooft on the demanding unitarity. I think we do get unitarity in different ways. No, we have a factor 2 debate. I don't know why factor 2 always appears, but we don't get the factor 2, we get the same result as Hawking. But the main difference is we arrange different vacuum at parity conjugate regions of physical space. The reason is a kind of, well, there's a theoretical motivation, but there is also an observational motivation. What kind of calculation precisely gives that exactly this thing, so that's also a driving force for us. But what I feel intriguing in all this studying all these historical papers on Professor Hooft's ideas and many, I was puzzled by, especially the inverted Harmonic oscillator is super inspiring for me. And when I look at papers in different journals, which normally high energy physics people don't look at in condensed matter systems, they study analog experiments with some kind of inverted Harmonic oscillator system mimicking Hawking radiation. It's the same eigenfunctions. They behave the same. So I think that's a good opportunity to explore. And baryon heating works are extremely interesting for me, and they are relevant for gravity. And I felt bad when I looked at explored the condensed matter systems after 10 years of my research life, knowing that condensed matter was so important in particle physics. I think that is something. Okay, anyway, past is past, whatever happened is happened. I think what I am super happy about this conference, we have brought together all the physics. That is very inspiring for me. So I'm sorry I went a bit out of what I presented. That's something that I would like to say.
Thanks. Okay, so the first thing I would like to say is that what I'm talking about is not quantum gravity, it's quantum plus gravity. So it is a different regime, and we are looking at different things, and we ask questions in a different way. We use different tools to standard quantum gravity. But there is a common, so there is a goal that is common with traditional quantum gravity approaches, and that is to see whether gravity is quantum and to see whether we can make sense of this question in some way. And so, as I mentioned, this is more like a bottom-up approach. So we take elements from quantum theory, we take elements from general relativity, we put them together, we reason in terms of thought experiments as a tool to test the consistency of the two theories we put together. And we try to basically to push the conceptual aspects of this theory to the extreme for what we can do, of course. And already there we find that there are some questions that arise that can be like what happens to the notion of time, to the notion of space, to the notion of locality. What does it mean to have, say, a global infinite space that we cannot factorize into a local tensor-plane structure? And these are all questions that become, of course, much more dramatic if looked at from a traditional quantum gravity approach, but you already see the cracks in this low energy regime, basically. And what we can do in this low energy regime is to come up with thought experiments to link them more directly to like some particular physical system that we can devise in the laboratory. And even if we do not have immediately now the possibility of testing that in the lab, then we can hope that we can do it in the future, and there are experimental groups that are trying to do that. So this is to say that there is a dialogue with the more traditional quantum gravity approaches, and actually this is also starting and it is reflected in terms of how the community is proceeding in this case. And the other aspect that we can include is quantum information. And I think this is also a very valuable perspective. As we have heard in the talk that Professor Genovese gave, we learned the lesson from Bell inequalities. And this is a very deep lesson about the fundamental structure of the theory and what it means that something is quantum. So quantum information gives us a different yet valuable way of proving quantumness and against a more general class of theory. So this is not the confirmatory approach that is taken in other fields of physics, but it is rather a first principle approach. So you come up with a list of principles and you show that one of them has to go if you violate a certain experiment. If you experiment and you go beyond a certain value, the CSH value. And then there are a lot of tools that we can import now because like quantum information theory as moved forward, we have many more results than what we had like 30 years ago. And so we can hope to import what we have learned there into some gravity research. But immediately, as soon as you do that, you realize that the very basics of quantum information does not apply to gravity because we embed it in space, because we have diffeomorphism invariance in gravity, because we have gauge freedom, and because, well, if we have quantum gravity, space-time relations fluctuate. And so we have to revise these concepts, basically to lift them above the necessity of embedding the theory in a classical space-time. And this is something that we do not know how to do currently. But we have hoped to revise the formalism and to come up with a version of all the quantum information results that does not rely on having space-time, because in the end, the core of quantum information is that this is an abstract framework that does not depend on a specific energy scale. So putting the tools of quantum information with the tools of gravity all together can really help. The problem is that the realization of quantum information is, of course, in a laboratory where we know what is going on. We have a space-time. And so this is a challenge that we have in front of us, and that I hope that we can make progress on this challenge by collaborating with researchers from different communities that have thought for a long time about what happens to space-time, what happens to time, what happens to all these locality, to all the causality, to all these fundamental concepts that we have to question and that we have to revise, I think, from the moment we start.
Thank you. So I think that the growing of quantum technologies in the last 25 years has a significant impact, also in connection with quantum gravity, at least for 4 different motivations. One was already mentioned by Flaminia, is the cross-fertilization between the two fields. So concepts of quantum information in particular can be explored in other fields, and for the information black hole paradox is one of the arguments of this kind. Also, the development of quantum technologies, of course, paved the way for experiments with unprecedented precision, quantum metrology in particular, and this can be a new way for searching for some, I won't say scale effect, but at least some quantum and gravity effects. And already Flaminia mentioned these experiments toward mesoscopic scales, and this is one possibility, of course. That is with nanodiamonds is one. There are also other ideas, for example, using micro and nano resonators and so on. But also for search, for example, for very small noise, like more graphical noise that was proposed by Craig Owen in his terminal experiments, based on very precise interferometers and eventually quantum enhanced interferometers. So this can be a role for searching for small scale effect that maybe has even more chances than just increasing accelerators, but anyway remains very, very far from plasma. The second important point, the third important point that was already mentioned also, is the fact that, of course, to understand better quantum correlations and entanglement is also very important for understanding eventually a new theory what could and should be. Now, for example, we know that if you wanted to have some theory, now Bellamy inequalities are unequivocally violated, so some of the, if we want to have a deterministic theory, we must anyway give out some other hypothesis of the theory. And this is, so new theories are also bound by these experiments and foundational quantum mechanics. And finally, the last point I would like to mention is that this entangled system also represents a platform for visualizing some effect that one can imagine. For example, we realized a few years ago, let's say visualization is not a proof of principal experiment, just a visualization of page-and-Butter mechanism of time as an emerging property of entanglement, where we had a system that was globally not evolving for a certain Hamiltonian, as would be for the Willard and Mill equation for the whole universe, but one can use a subpart as a clock for the rest of the universe. And this visualization can also be an help in elaborating new theories and new models. So I think that the cross-fertilization between quantum technologies and quantum gravity could be very important.
Thank you. So now we open the floor to questions. There were some questions from the morning, and of course you're welcome to direct your questions to the speakers. Yes, please.
So, sorry, you referred to Gia's question. You mentioned that in quantum information there are different notions of the quantum tensor, but the figures one of them because I'm not really familiar with the situation.
So specifically in this field, people have a different threshold for what they would consider as something that is quantum. So Feynman's definition was I have the gravitational field in a quantum position state. So this is what he used. Then there are some people who take a more quantum information approach that say the gravitational field is not a lossy C. So it means that it cannot transmit, so local operations and classical communication, that's the acronym of LOCC, cannot generate entanglement. And if you have something that generates entanglement and you are in the assumptions of the LOCC theorem, then you conclude that the channel basically is classical. So in this perspective in which you view gravity as a channel that you get a classical or quantum, and then if it generates entanglement, it's not an LOCC channel. Then there is another level that you can use that is, well, actually the only real signal of quantumness is if I observe the single gravity effects. And this is a pretty high bar to set experimentally because, well, according to some people, it's even impossible to measure single gravitons. And basically, this is what John Closer did for the electromagnetic version. So he had a single photon experiment, and then he showed that this cannot be explained by any semi-classical model. And this is, of course, something that in the electromagnetic case now that people every day in their office single photons. But before we have single gravitons, maybe never, I don't know. But in the meantime, quantum technologies have moved forward, so maybe there is a smarter way of reaching an analogously compelling conclusion for a gravitational experiment. And I do not know what that would be, honestly. And then there is the Bell way of saying when something is classical or quantum, that is laying down a set of principles that identifies a classical theory and showing that experimentally you violate one of these principles. So basically, and even if you look at definitions of quantum that you give just in quantum mechanics, or classics, what is not classical, say the RFS theorem, quantum integral, commuting measurements, and so on and so forth, these do not coincide. So you have different ways of saying something that is quantum or classical, and you can classify some cases that are quantum according to one definition and not according to a different definition. So, the very definition of what we consider quantum or classical depends on the context that we use in this.
So, Flamini, if I ask a follow-up question, so what you did basically was you calculated a one graviton exchange, basically. When you looked at the actual.
You can read it as offset gravitons.
Yes. Yeah. So it's essentially a one graviton exchange. Now, and also as you notice, if you take the static limit there, you recover the Coulomb potential.
Yeah.
Okay.
For the source that is in a quantum superposition of localized states.
Yeah. So now, would it make sense to say that if you, on the other hand, if you claim that, okay, the Coulomb potential part is essentially classical and it will not induce entanglement, then it would make sense to retain a part of the amplitude which is kind of not Coulomb. So what if one looks at relativistically moving particles? Where the static limit, from the static limit you recover the Coulomb potential. If you look at relativistic particles, you would expect that you would retain another part of the amplitude which is not the same as the Coulomb interaction.
Yes. So if you want to solve that so my PhD student is looking into the generalization of these to moving the sources, basically. So it turns out that as soon as you consider, so basically all we have for matter in this case, also for the usual gravitational induced entanglement proposal, is a T00 effect. Basically, you are Tij, you don't have it. So you have to consider Tij now if you have a source that is moving, and immediately as soon as you switch on the TIJ, then the situation gets technically much more complicated, and especially if you want to consider a fully delocalized source. Why? Because you have Schwinger terms. And so the trick that we use to solve the gravitational field there, that is to solving the energy eigenbasis, cannot be used anymore, because basically the field does not commute at different spacing conditions. And so you need to come up with a smarter way of solving the field, and this is really not trivial at all. And so basically what we are doing now is to solve it in the quantum superposition of, say, localized trajectories, so in the limit in which at least you can consider the source undergoing a superposition of classical trajectories. And in this case, you can solve it at least technically. And I do not know, so the other approach that you could use is to consider first order relativistic reactions to tame basically the Schwinger terms in this case. In the full relativistic regime, I do not have a good way yet to solve the general state of the sorts.
What if you follow not a more kind of clever approach, but a more dumber approach? Like just couple gravity to the scalar field theory and calculate the amplitude of the scattering amplitude between two heavy scalar particles. And then the scalar particles, you go back and put them in the superposition state.
Yes, so scattering amplitudes, you can always do it. This is not a problem. The problem that we encounter is that in this tabletop experiments, you want an explicit description of the quantum state of the gravitational field that sources to get the phase, basically. And in this case, you don't do the same calculation as in scattering amplitudes.
Question, and my question is inspired from also her learners was that controversies are good sometimes to progress. I know Bell inequalities kind of understand, but there are objections and loopholes in the Bell inequalities which Herod mentions. I never understood. If you can understand this.
Yes, well, I find quite difficult to accept that Bell's general argument is that it's quite clearly formulated the notion of statistical independence, which he postulates also in the time dimension. That is to say, he assumed that the initial state contains all sorts of particles in a random position, and those positions should not be correlated in any way with what they later do. But as a physicist, I say not only there are lots of what I would call micro correlations, as to say at the microscopic scale, there must be all sorts of correlations, because any given configuration of particles now should give you one given particle configuration in the future. That is, if you believe in variables, or if you believe in a classical explanation of the quantum phenomena that we all are studying. In that case, the laws are strict, and any given position of the particles now will lead to one and only one given position for these particles in the future. Then, of course, these positions are correlated. That's what the equations of motion say. So, to postulate that these equations are totally uncorrelated is, of course, putting in the answer that you want, which is that quantum mechanics cannot be explained in classical terms. No, it cannot be explained unless you take the classical theory seriously. You should take as seriously as the classical laws of nature. If you throw water from one bucket into another bucket, and you can calculate exactly how it flows as accurately as you want, well, you won't reach infinite accuracy in the case of water because there are too many molecules around, which you cannot possibly accommodate for in your calculations. So no, we cannot do those calculations. But that's not my question. My question is, does nature itself use complete equations for the evolution? I think that is a very important question. According to quantum theorists, they say no. Even if you would know everything that is to be told about electrons in the beam pointing towards each other, then still, if you try to compute how these electrons collide with each other, they still produce a statistical distribution. That's the claim of quantum mechanics. And I think, well, that is correct, as long as you don't know the exact physical equations. But imagine some super being who would know exactly every single equation of Weber and its particle to infinite accuracy. Then there's no room for statistics anymore. Then every outcome from the calculation should be just one particle comes there, and that particle goes there, and that particle has decayed, and so on. So this kind of stay that way. Of course, we can't hope ever as physicists to get such an accurate description. What we can hope for, and I think quite reasonable, is to suspect that nature itself works with such equations that everything in principle is fixed. But to assume that everything in principle is statistical, then you've assumed the result that Bell thought to be arrived. So I never quite went along with his inequality, and that means that there are no hidden variables.
I can just add my point of view, but I think it's the point of view of most of people working in this field. No? So to say if no particular position of every position and momentum of every particle in the universe, it can predict exactly what will happen in the future. No? This is classical mechanics position. No? So somehow this is hidden variable. If I know the hidden variable, everything is predicted. And so what Bell said, these are exactly the three hypotheses I mentioned. No? There are hidden variables, okay, but this is not sufficient. Should not be no local transmission, because otherwise the apparatus is so fancy and both can communicate each other. And finally, there is possible to have random choices of the apparatus. So I can have Alice and Bob having a random choice of the apparatus. Of course, there is, if you want a further additional hypothesis, I can produce independent states at the beginning, but the hypotheses are the basis of all the physics. I can build systems and make experiments. So what does it mean, the violation, experimental violation of any hypothesis? One of these hypotheses is wrong. If I want, if I want to keep, let's say, a vision where everything is predetermined, I can do because it's only one of the hypotheses, but I should suppose that something else is violated. So, for example, the apparatuses are not anymore independent. Okay, this is possible because in a superdeterministic theory, everything can be predicted since the beginning. Also, the status of the apparatus. Of course, so what Bell is saying is that if I make these three hypotheses, I have a limit on the value. I observe a violation, which is in agreement with standard quantum mechanics. Standard quantum mechanics, of course, say everything is probabilistic. I don't have a predetermined value of the observable. This is not the only possibility. I can also build other theories, even deterministic, but I must release one of these hypotheses. So, perfectly fine for a deterministic theory, but with this kind.
No, but here you mentioned the freedom of the observer to choose what measurement to do. That's obviously totally impossible in a deterministic theory of the kind I was thinking about. Because every particle can only be in one spot. If you want to change the settings of your detector, which is an important point in that case, you have to start with a different emission condition. Then if you don't change it, you can't use the same atoms with the same distribution of photons and everything, and just only make it the change in the setting. Where does the change come from? You can't just have that in a deterministic theory. And then I think once you take that, you remove that out of Bell's argument, then you remove the bottom of the theory. So again, there's nothing to claim anymore. So the freedom of choice is a very big axiom, which to my mind, totally impossible in a deterministic theory.
Okay, I think freedom of choice maybe is a little bit too specific. I would say possibility of an independent choice of the apparatus, even determined by some random phenomena, if we admit exist random phenomena in nature.
I think there's an even more basic objection in there. It's just a basic fact of radioactivity. You see nuclei which are rigorously identical. No experimental choices. In principle, you can check that they obey quantum statistics of identical particles. I don't know if it's actually been done, certainly do it. And yet they decay at different times.
Yeah.
Period. I don't see the need for Bell, any complication. It's really very simple.
But you can have a hidden variable determining the decay.
No, you can't, because the particles interfere. There can't be hidden
But
variables.
yes, but in the hypothesis of hidden variable, they are not really exactly the same. There is some hidden variable you don't know.
But if you do the kind of experiments that show the identity of particles, quantum statistics, which you can test experimentally, has been tested.
Yeah,
In
but-
many ways, they are rigorously identical. Otherwise, you couldn't have these superpositions of states that were inequivalent.
Yeah, but at least in principle, you could still build a distribution reproducing this kind of experiments where you have an hidden variable and you do not have access to this hidden variable. While in the Bell inequalities, you can. You have mathematical proof you can. In this case, you don't have a mathematical proof you can.
Yeah, thanks. Yeah, I think it's my duty to comment on this again. I mean, not just what we heard about that were presented here, these experiments, but in general, the tables of experiments that claim that they can detect quantum gravity with current technology. Okay, my statement is that the chances of that is exactly zero. Well, exponent is 10 into the power minus 66 or something. Not exactly zero. Now the typical, I've seen several papers and proposals and talks that claim this, and usually they make some typical mistakes. So the mistakes are they confuse multi-graviton effects with single graviton effects. Now there is no question what classicality means. Classicality are the effects that survive in the limit when we take h bar to 0, and those are the phenomena that deal with many particles, and those are the ones that compensate the suppression. Now, in case of gravity, the problem is even more severe because quantum gravitational effects are tremendously suppressed by coupling of a graviton. So you need really tremendous number of gravitons to have any effect. The reason why we see classical gravity because, for example, gravitational wave, because it has huge occupation, coherent state with huge occupation number of gravitons. That's why this compensates the quantum gravitational suppression. So once you understand that, you see that these experiments are completely hopeless. Another mistake they're making, they think that if you increase the mass of a sample, you increase quantum gravitational effect. This is completely wrong, because when you increase mass of the sample at the expense of having macroscopic object, you don't increase quantum gravitational coupling. Because otherwise this building would be a great probe of quantum gravity. It's much heavier than the Planck scale. So that's another mistake. And but what really shocks me in these presentations and proposals is that a little bit sort of non-appreciation of the magnitude of the problem that they are claiming that they can bypass. Because, for example, first you need to entangle macroscopic objects. That would be a revolution on its own without any quantum gravity. Okay? But this is usually mentioned en passant. Okay, we entangle these macroscopic masses as if this is very easy. This is exponentially difficult. Then on top of that, you need to generate entanglement through gravity and through quantum gravity. So I think this is a triple revolution, which, okay, my prediction is that this will not happen in the near future. Okay, maybe we're lucky we can detect some quantum gravitational effects. If the quantum scale of gravity is very low, it cannot be lower than TeV energies. So maybe LHC or some other future colliders, they can hit the strong quantum gravity scale. Yeah, in that case, maybe we have a chance to look for it. But this will not, in the tabletop experiments, at the length scales that they operate with, this is absolutely hopeless. So that's my statement. So.
I'm not sure I understood what the problem is that you mentioned now. But I can give an example of an experiment which in principle can be done, not in practice. So I'm not proposing anything but a unit experiment.
Yeah, my problem was practical problem. In principle, of course, there is one problem.
No, but
Please,
let me show
yes.
the experiment on Kudu, and then we can argue about it. The experiment on Kudu in principle is take a very strong magnetic field that ranges over a very large distance, and you send a photon through that magnetic field. In the strong magnetic field, the photon will be coupled with the graviton.
Yes,
so
but you need such a
the
field.
photon goes in, the gravity comes out, then the barrier is sort of no photon can go through, and then you can do the opposite at the other end, the graviton turns back into a photon. If you see the photon coming, then you have done a quantum gravity experiment.
Sure, but you need such a field, and you need such a setup.
So for pragmatic reasons, as I said, you need light years of strong magnetic fields. We don't have that in our laboratory.
Yeah, I agree with that.
So of course, but still, in principle, this would be a possible experiment.
Yeah, in principle, of course, that's the problem with quantum gravity. That is doable in principle, but in practice, with current technology, I think every proposal I have seen is hopeless. Now, maybe tomorrow someone will come with a better proposal. For example, manage to create this very coherent, very strong magnetic field as you mentioned. Sure, yeah, in that case, I'm not discouraging anyone to come up with proposals, but I just want to, I'm complaining about wrong proposals.
Me? Okay, so I spoke on the first day, and I can tell that my talk has been widely ignored. I'd like to go back to one slide that I skipped over in the interest of actually finishing on time, that I think can be very helpful in these discussions of what quantum gravity is all about. So this is one slide, quite quickly, but I think will really aid the discussion. So this is a slide that talks about levels of quantum gravity. It's not as if quantum gravity is one subject, as if quantum anything is one subject. There are different levels at which it can be discussed. So to make the different levels clear here, I've in blue given their electromagnetic analogs where there's a rich experience in literature. So first level is quantum behavior in gravitational potentials. So this is the kind of experiment that people do in neutron interferometry, where you have neutrons going in different places, and someone goes up, one goes down, and they interfere, and you test the quantum mechanics is obeyed in that case, even though it's a gravitational potential. The electromagnetic analog would be independent particles moving in mean fields. The next, which I think is the level at which is the level of quantum behavior in gravitational potentials of quantum variables, where it's important to treat the sources as quantum mechanical variables that you can superpose. They have different effects in different parts of the superposition. This, in quantum electrodynamics is the level at which we do quantum chemistry, excluding photochemistry. So quantum chemistry that doesn't have photons. So it's quantum electrodynamics, but no photons. The next level is accessing properly gravitational degrees of freedom as real particles. This is what's done, of course, in gravitational wave detection on the gravity side, and in electrodynamics, there's the domain of photochemistry, optics, and importantly, quantum optics. think the analog of quantum optics is something that I talked about on the first day, and I think can be very fruitful and is right for the application of modern quantum technologies. Then there are other levels. One is accessing properties of gravitation or virtual degrees of freedom as virtual particles. This is the domain of taming infinities and calculating radiative corrections. Thanks in large part to Professor Prost's work, we know very well how to handle that in quantum field theory, but in gravity, not so much. And then finally, there's the question of whether maybe there are other levels. Maybe there's space-time foam, maybe there's space-time matter that unifies everything. There's an ether, maybe there's an information superhighway somehow connected with fine gravity wormholes. In electrodynamics, we also have discussions of other levels, unification, subsuming that also into a theory of everything. This is just sort of to make room for other things that aren't clearly as yet connected to experiment as the first 1, 2, 3, 4 levels. So that's my way of organizing the discussion of what we mean by quantum gravity.
I have a point to the last point. Indeed, early universe CMB or primordial gravitational is another arena, because when we have inflationary expansion, we create from back fluctuations, and these fluctuations are separated apart to super horizon scales. That is actually the one area where we can test entanglement more.
I think that could fit into level 3.
Yeah.
What I've been trying to explain is my view that quantum mechanics is not a theory about forces, about particles, or about experiments, but quantum mechanics is a language. And the language says that a system being in this state will evolve into a system being in that state. That's all you have to say. And whether a particle gravitates or has Coulomb interactions, the same is true. The particle sits here now. In the future, it will be in that state, and we can try to compute as accurately as possible what that new state is. And quantum mechanics is an extremely useful language to do that. You could use the same language for gravity, but as I also claim, you don't have to. There are models which are both quantum mechanical and classical, in the sense that they both quantum mechanics as a language and classical theory as a language give you the same answer as to how the thing evolves. I call that model the pendulum clock, the quantum pendulum clock. It's just something where quantum mechanics can be used, or indeed does not have to be used in order to understand how it evolves. My suspicion is that all of this world, all in nature is of that kind. And if you use quantum mechanics, if you have available the exact complete language to be used to describe how things evolve, then quantum mechanics is not needed anymore. It may be useful to use it, but particularly for statistics, but not for explaining how the world works. That explanation, I think, can be done with classical equations. That's a big if. I couldn't prove that, of course not, but I'm now making some effort to make that theory work better than it works now.
Yeah, so I agree with your classification, and so I think it's a good way of looking at that. And I would just like to add that we should also have so you made the gravitational and the electromagnetic equivalent, and you mentioned quantum optics, and I think that we have also a lesson to learn from quantum optics and from all the developments in quantum optics. The idea is that like what we can learn when we actually perform an experiment, and this is also a very important thing, because the fact that we can write down some equations and then find the experimental outcome does not mean that the result of this experiment, as Daniel Palmis tells us, basically definitely concludes that the way we have written down the equations is correct. So we need, in going the opposite direction, we have a lot of subtleties, and we have to consider, for instance, how the device, how the measurements are made. And this is something. So quantum optics people usually are the more purists in telling what you can conclude from the outcome of an experiment. And since in quantum gravity we are on very shaky grounds, then we also have to be careful about the opposite implication of the experiment that we're making. So that's the only thing I wanted to add.
Maybe I'll ask the last technical question from quantum engineering. The technical question, so the answer will be short. In your first slide, you showed the difference between a weak experiment and a different not weak, because of the bioequations thing. So I think if I understood correctly, the beams were kind of completely separated. That was not a weak experiment. If they had an overlap, they didn't have a weak experiment. Sorry, I switched. Thank you. So then I would think that in the delayed choice quantum linear type experiments, the beam splitting, that will be classified not as weak, isn't it?
Oh yeah, okay. Yes, of course. Then at the end you have you can always still erase this information.
Yeah, so that was my question. That if
Yeah,
the information is
in the quantum eraser,
yes.
of course, at the beginning you have a perfect separation,
Yeah.
but then you erase this information. So up to when you don't have, let's say, a macroscopic apparatus acquiring the information and everything remains quantum, you still have the possibility to erase because everything is unitary. Only when you have a macroscopic apparatus, at this point you have non-unitary interaction, the information is acquired. And so, yes, of course, this separation is not yet a projective measurement.
Yeah.
Projective measurement, at the end, you have a macroscopic apparatus.
Yes, that was my question. That just the fact that they are separated is not a projective measurement.
It is what is needed for a final result.
Okay. Thank you.
You're welcome.
Okay, so I think we end the session now, and people could go for lunch, and we can thank the speakers.
Before going for lunch, they're going to have the group